Okay, welcome back again. Now we are discussing another application of Ampere circuit law. So in this video we are coming to the magnetic field which is produced by a current carrying solenoid. As you can see in the figure here on the board. Now here this figure shows a solenoid, that is a coil of wire having number of turns, having n number of turns, which is wound up on the metallic frame, that is constituting a solenoid. So the solenoid is here on which the current carrying wire is placed or the wrapped up, and the circuit is completed at the base, that is at the bottom. So we can see here the battery is inserted. In the figure we can see battery is inserted and the solenoid is completed. Now also for our understanding we are considering a metallic rectangular loop, that is having the names ABCD, and this AB is taken along the axis of the solenoid. Okay, so AB is taken as the axis of the solenoid that is passing through the center of the solenoid. So this is all about the figure we have to imagine. Now the portion DC of the solenoid is outside the DC of the rectangle loop what we have considered, that is going outside the solenoid, and the AB is just passing through the center, that is the passing through the axis of the solenoid. Now we need to consider this AB portion. We need to find out the magnetic field due to this solenoid at a point which is located well inside the solenoid. We are not considering about the field which is present outside, because outside the field is very weak. We have to find out only the magnitude of the magnetic field which is present inside the solenoid at a particular point. So for this we have imagined one rectangle ABCD. Now we come to the derivative part. So consider a very long straight solenoid having n turns per unit length. Now here we are taking small n. If we take small n, that means the length per number of turns per unit length, and if we take capital N, that will be the total number of turns. So just to be careful about the difference. Again I am telling capital N is for total number of turns in the solenoid, and if we divide this capital N by L, that is the length of the solenoid, we will be getting small n, that is number of turns per unit length. So in this derivation we are taking n number of turns per unit length, and the current carried by the solenoid is I. Now let us consider a point well inside the solenoid at which the magnetic field is to be found out. Now for this we have imagined AB equals to L, that is the length of the rectangular path that is inside the solenoid. Now the number of turns enclosed by the rectangle, will be n into L, that is equal to capital N. I told already capital N is the total number of turns which is the product of small n and L. Now after this the total electric current flowing through the rectangular path will be taken as NLI. The total electric current will be taken as NL, that is total number of turns multiplied by the current value of current, that is I. Now according to Ampere's law, as you can see on the board, integration B dot dl equal to mu naught NLI. Now we know that Ampere circuit law says that integration of closed integral B dot dl equal to mu naught I. So in place of I, now we are writing NLI because that is the current flowing through the solenoid. So integration B dot dl, as you can see in the expression on the board here, that is integration B dot dl equals to mu naught NLI. Let it be condition number first. Now for the closed loop ABCD, we are taking the whole complete loop. Integration B dot dl equals to integral A to B dot dl plus integral B to C B dot dl plus C to D B dot dl and plus integral D to A E dot dl. So we are splitting this whole loop into four different parts. We are splitting the rectangular loop into four different parts, taking one side at a time, that is A to B, B to C, C to D and D to A. Now the side CD is lying completely outside. As you can see from the figure, again the side C to D is lying completely outside. Now the sides BC and DA, they are perpendicular to the horizontal, that is perpendicular to the horizontal, and the direction of magnetic field is horizontal. The direction of the magnetic field B is like this. along the axis, and the components BC is vertical, DA is vertical. So these components are making angle of 90 degree with the direction of the field. Direction of field like this, direction of BC, direction of DA. These are making 90 degree angle. So in this case, in these two cases, theta will be 90 degree. Again, come to the mathematical part here. The direction, you can see the second last line in this screen, as the direction of DL and vector B in path BC and AD are perpendicular. So B to C, B dot DL, and integration D to A, B dot DL become 0. Now near the ends of the solenoid, the field lines are crowded. We know that near the ends of the solenoid, the field lines are crowded, and outside the field lines are far apart from each other. So the portion CD is lying completely outside the solenoid, and the field lines are far apart with each other. So the magnetic field will be very weak outside the magnet, that's outside the solenoid. So this part can be ignored. That means magnetic field is very weak outside the solenoid. Now we are having four cases: A to B, B to C, C to D, and D to A. Out of these, the perpendicular ones cancelled. The perpendicular for this one and this one, they are being cancelled since angle is 90. This one is outside, that is the upper one. You can see the figure again. The upper one, that is D to A, that is C to D. C to D, that is also cancelled. Now we are left with only that part which is along the axis of the solenoid, that is A to B. So now we have, again, see the expression, integration of B dot DL equals to integral A to B dot DL plus 0 plus 0 plus 0. So all the three other components become 0 here. Now we are getting finally integration B dot DL equals to A to B integral B dot DL. Now since in this horizontal case, the direction of B and the direction of DL are same, so we have B dot DL equal to BDL cos 0, and cos 0 become 1. So we have B dot DL equals to again B into DL. After this, simplifying this expression, integrating this B dot DL within the limits from A to B, we get integration of B DL. Now B is constant magnetic field, so it can be taken outside the integration sign, and integration of DL becomes the length AB. Integration of DL will become A to B, complete length of the solenoid. So AB can be taken as L capital. So we are having now next expression, integration of B dot DL, that is becoming BL now, as you can see in condition number 2. So now from 1 and 2 equations, we have BL equal to mu naught NLI. We are comparing equations 1 and 2. We have BL equals to mu naught NLI, and so L is cancelled from both the sides. We have final expression B equal to mu naught Ni. So this B equal to mu naught Ni is the expression for the magnetic field due to a solenoid at a point which is present well inside the solenoid. So this finish our derivation, that the magnetic field we have found out due to a solenoid at a point which is located inside. Now we come to next topic, that is toroid, in the next video.